Okay, physics crew, question 5. Let's do this. We've got a very typical setup here. We've done this in class. You've got a piece of card. You've got a wire going through it. Okay, now if we put a plotting compass on the piece of card, those little compasses that we use, then it will obviously point north when there's no current going through the wire. The question is, what direction will the current go? What direction will the compass point if we put a current through the wire? Now what you need to remember here is that whenever we get a current, we get a magnetic field. So if we've got a hole in this piece of card, we've got this piece of wire going through. If we put a current through it, we will get a magnetic field acting in a circle around this wire. And so if we were to put a compass here, we can see that we've got a straight line going through that. So either the magnetic field could be going in this direction or this direction. If we zoom in on this bit of the magnetic field and we pop the compass there, we've either got an arrow that way or that way. And given that in the possible answers to this question we've only got we've got this as an option, that must be the way that the magnetic field is going. It can't be pointing in any other direction, like this. It has to be going with that concentric circle. Okay, now next question, that's for 1 mark, so A for 1 mark. Now we're moving on to A part 2. This is a 3-mark question, and it is a investigation question which students often find really, really difficult. This is going to sound obvious, but you have to just try and as clearly as you can describe what you would do. So how would you do this investigation? You need to state what you would do. There's a couple of possible options. We go with the idea that we've got one plotting compass and we could do the investigation that way. You could use multiple plotting compasses and put them on the card all around the wire, or you could use something different like iron filings is often what we use for tests on magnetic fields. I'm going to stick with what we've got in this question, which is one plotting compass. So for the first mark, I'm going to say place plotting compass near the wire and record direction it points. Okay, so now we've got a start. Let's say we have a top-down view. Let's say that's the wire coming out of the card. We place the plotting compass here and maybe it points in this direction. We then move compass to, that's going to be 1 mark there for that first bit. Move compass to a different location and record direction. I might be being a bit over thorough, but let's make sure we get those marks. So maybe we move it here, and then we're going to repeat that process. Just put that as an extra because we're going to maybe do that all the way around, and then we're going to make sure we get that 3rd mark. Join the arrows together to show the field, and so we'd do all that and we'd get these concentric circles. Okay, excellent. Next question. Another multiple choice. We have a wire going through a magnet. We've got a north pole, we've got a south pole. We've got a wire and we're told the direction of the current is this way. So we now need to remember our left-hand rule, and we need to remember the direction that a magnetic field goes. So first let's look at the magnetic field. Now this is quite confusing, but if we remember, the Earth is a bit like a bar magnet, okay, in terms of it has a north pole and a south pole. But the real key thing here is that we've got to remember that the north geographic, so our geographic north, the bit that we call the North Pole, is actually a south magnetic pole. Okay, so north pole, north geographic pole is a south magnetic pole. What does a compass do? It points to the north geographic pole, but therefore it's actually pointing to a south pole. So when we draw in a magnetic field, it's going to go towards the south pole like so. So that's going to be the direction of our magnetic field. Here is our left-hand rule. Now, what we just need to do is put our thumb and our first finger at right angles to each other like so, and then our first finger and our middle finger at right angles to each other. So hopefully you can get the picture there. And then we remember our Federal Bureau of Investigation, FBI, F being the force on the wire, B being the magnetic field strength or the magnetic flux density. You just got to remember it's B, I'm afraid. And then I, also one you had to remember is current. So what we need to do is now arrange, and if you've got to do this in exam hall, you've got to do this in exam hall. Let's arrange ourselves. So this finger is the direction of the magnetic field, so that needs to go along like that. Haven't quite drawn this diagram perfectly. And then the current is going that way. So hopefully you can see that my thumb's coming up towards you. So up is the answer to this. There is a force on the wire upwards. And so that's going to be B. And then B part 2, question B part 2, is a 1-mark question on saying or comparing the forces. What are the two forces? There is an interaction between the magnetic field produced by the magnet and the magnetic field produced by the current. What can we say about these forces? Well, now we're going back to year 1 and we're going back to Newton's third law. So forces are equal in size or magnitude and opposite in direction. Newton's third law. Every action force has an equal and opposite reaction force. Okay, last but not least, we've got a calculation. So let's have a little look at this. If we have a wire with a current going in this direction and we have a magnetic field, we'd draw it continuing, but I'm just kind of showing you there. So this is the field, this is the magnetic field, this is the wire with the current, and we are given some information. So what I would encourage you to do is write all the things down the side that you have or that you're trying to work out. We have a force, magnetic flux density, magnetic flux density, the current, and the length of wire that's in the field. Now, actually, what I would encourage you to do is not write all that out. What I encourage you to do is do F, B, I, L, and then write down everything you have and everything you're trying to work out. So we're told that the force is 0.045 newtons, that the magnetic flux density is 0.72 newtons per meter. Current is what we're trying to work out, and the length of the wire is 30 millimeters. Okay, we're going to remember our units in a moment. Now, I'm not going to go into great lengths on rearranging equations at this stage. If you want a video on that, then request it and I will get round to it. So I want to get I on its own. We're going to divide by B and L, and that's going to give us I equal to force divided by B times L. Okay, I've just brought these two underneath. Alright, so let's substitute in 0.045 divided by 0.72. Now, got to be careful. If we put 30 in, we're going to lose a mark. This is a 3-mark question. What we need to do is divide that by 1,000, because of course that's millimeters and we need it to be in meters. So like so. Let's do that. I'm just conscious I'm going slightly over time on this, giving a bit more explanation for some of the things, but let's do that. Not times, apologies. All right, 0.145 divided by 0.72 times 0.03. And I'm going to leave it as I have done always. So the right number is significant figures, which is 2.1 amps for the current. But if you leave it like this, you will get all the marks unless it specifically says to leave a certain number of significant figures, which it doesn't, but there we go, 2.1. Thank you. I'll see you for the next one.